Hello, and welcome to the AI Research Roundup. I am Alex, and today is May 20th, 2025. We are diving into a paper titled Chain of Model Learning for Language Model, which popped up on Hugging Face's trending list just a few days ago, published on May 17th. This research paper introduces a novel learning paradigm called Chain of Model, or CoM. The core idea here is to structure models with a chain style in their hidden states, aiming for better scaling efficiency during training and more flexible deployment. It achieves this using what the authors call chain of representation, where hidden states are essentially combinations of linked sub-representations or chains. Alright, so to visualize this chain of representation, take a look at Figure 1. Part A shows a typical representation, like a standard hidden state in a model. A hidden state is an internal feature vector that a neural network layer computes, capturing learned information from the input, and then passes this information to the next layer. Then, Part B illustrates the chain of representation. Here, the hidden state is actually made up of several linked sub-representations or chains. In this example, 3 chains of different scales. This structure is key to how chain of model works, allowing for progressive scaling. Okay, building on that idea of chained representations, Figure 2 here gives us a nice visual comparison. On the left, in Part A, we see a standard linear layer. A linear layer is a fundamental component in neural networks that performs a linear transformation, essentially a weighted sum, on its input data. Notice how every input node connects to every output node. Now contrast that with Part B, the chain of linear layer. Here, the connections are structured into these chains. An output chain only processes information from its corresponding input chain and any preceding ones, establishing what the authors call a causal relationship. This chain of linear structure is central to the chain of language model. So, carrying that chain of linear concept forward, Figure 3 illustrates how this applies within an attention mechanism. Part A shows a standard attention setup, where input is processed to generate query, key, and value representations, which help the model weigh different input parts. Part B, chain of attention, applies the chained structure to these query, key, and value linear layers. Then, Part C introduces a key optimization called chain of attention with KV sharing. Here, the key and value components are computed just once from the first chain, and then shared across all others, which can really accelerate processing. Alright, now let's look at Table 1, which shows how these chain of model approaches, specifically chain of language model and chain of language model AIR, stack up against a baseline on common sense reasoning tasks. Performance here is measured using the ACC norm metric, which is essentially a normalized accuracy score for each task. We can see that chain of language model, for instance with a 1616 chain configuration and 2048 dimensions, achieves an average score of 45.27. This is very close to the baseline's 45.11, showing comparable performance, while chain of language model AIR offers that key KV sharing benefit we just discussed. Okay, so Table 2 then really drives home one of the big advantages discussed, progressive scaling. Progressive scaling, or chain expansion, is this idea of incrementally making models bigger and better by adding new chains to already trained ones. You can see here for both Tiny LLAMA and Llama 3.21b, when they add an expansion, essentially more chains, the average performance on these common sense reasoning tasks goes up. For Tiny LLAMA, it jumps from 57.43 to 58.35, and for Llama 3.21b, it goes from 60.39 to 60.53. This demonstrates the ability to improve models without retraining everything. Building on that ability to grow models, Table 3 showcases another advantage, elastic inference. Elastic inference is the capability to derive multiple, smaller submodels from a single, larger trained model by using a different number of its chains. Here, for a chain of language model AIR with a 1616 chain setup, using both chains gives us a 0.86 billion parameter model, with an average score of 43.90. But if we use just the first chain, we get a much smaller 0.33 billion parameter model that still performs respectably at 41.13. This flexibility is pretty powerful. So this ability to create smaller, efficient models through elastic inference really highlights the core innovation, the chain of model learning paradigm. This paradigm, often abbreviated CoM, is a new way to structure models using linked chains of information. When applied to language processing, it results in chain of language models, or CoLMs. We have seen this chain structure allows for impressive flexibility, like progressive scaling and elastic inference. Overall, chain of model offers a very promising route to more adaptable language models. That is all for this research roundup. Thanks for tuning in, and I am Alex.